Hi, I'm Jiachen. This video introduces our work, HEAT, Holistic Edge Attention Transformer for Structural Reconstruction. Structural reconstruction takes an image of man-made structures and produces CAD-level reconstruction with corners and edges. A typical family of tasks is planar graph reconstruction. For example, outdoor architecture reconstruction from satellite image, or floor plan reconstruction from point density image. 3D wireframe reconstruction is another structural reconstruction task, which simultaneously estimates the depth of edges. We'll focus on the first two planar graph reconstruction tasks in this paper. Existing approaches consist of two families of methods. The first family is end-to-end neural architectures, which generates all predictions in one shot. The inference is fast, but the results sometimes violate geometric rules due to a lack of geometry learning. LCN and ConvMP are typical examples. Another family, hybrid approaches, uses neural networks to get image features and rely on sophisticated search to enforce geometric regularities. They're usually very slow, but produce high-quality geometry. Montfroy and Explore Classify are recent state-of-the-arts. Our goal in this paper is to design an end-to-end neural architecture with improved geometry learning. We start by reviewing and analyzing existing end-to-end approaches. A standard pipeline applied by these approaches is edge enumeration and verification. Each pair of corners form an edge candidate to be verified, and I will show some examples here. One important limitation of existing works is that they usually lack effective geometry learning. Edges are either verified independently without considering the relation, or there's only restricted message passing within convnets. Our proposal here is to use compact 1D representation to encode both the image and coordinates information of edges, and then use transformer decoders to model the relations between the edges. Another problem of existing approaches is that the image patterns usually dominate the learning process. As shown by the examples here, most training samples are easy and can be directly answered by image features. However, when the image contains ambiguities or the structures are complex, the model could fail, but the overall training loss is still low as the samples are rare. The model is not pushed hard to learn the relational patterns between edges. To alleviate this issue, let's first think about how human can do structural reconstruction. Actually, human shares geometric common sense over man-made structures, and we can infer a plausible set of edges from corners, even without looking at the image. We know which kind of substructures are common in building architectures. For example, we'll infer a set of edges like this. Although the results might not align with the real image, we know which kind of structures are impossible in real world, and we never draw this. To mimic this ability of human beings, we want a model that can do structural reasoning without image, and can also incorporate image features naturally. With all these intuitions ready, we now show the overall pipeline of our method. The first step is edge node initialization. HEAT also starts by enumerating all pairs of corners to form edge candidates. We use the frequency-based encodings to encode the coordinates of the edges. Step 2 is the edge image feature fusion and edge filtering. Edge nodes extract image features from the feature maps produced by a convnet backbone, and we filter out easy negatives to reduce the computational cost of future operations. The image feature fusion module for the edge nodes is inspired by deformable attention. Each edge predicts its own sampling locations and weights for efficiently extracting corresponding image features from multi-scale feature maps. Step 3 is the final edge inference with weight sharing transformer decoders. The image-aware decoder takes the fused feature of the edges, conducts self-attention, and dynamically updates the image features in each decoder layer. However, it doesn't necessarily use the structure patterns in the coordinates features. So here comes the second decoder, the geometry-only decoder, which only takes the coordinates features from node initialization and has no access to image. It shares all the weights with the image-aware decoder and only used during training as a regularization. And with this overall architecture, we fulfill the proposals that we discussed before. HEAT is trained with a mask training strategy, which further encourages the transformer decoders to exploit the relation between edges. And the inference is conducted iteratively, starting from the most confident ones to harder ones. Note that only the image-aware decoder is used for inference. On outdoor architecture reconstruction, we outperform all existing approaches from different families, and the qualitative results are visually pleasing. Our indoor floor plan reconstruction were comparable to the state-of-the-art hybrid approaches, but need much less running time. And our results are much better than existing end-to-end approaches. Thank you for watching. Please find more details and results in our paper or check our project page.